So good morning. In our last class, we studied the closure properties of functional dependencies. So today we shall discuss few algorithms related to these functional dependencies. So the first algorithm here we will be studying is to find the closure of a functional dependency of an attribute. So here, so if x is any attribute, then we have to find all the functional dependencies where x can appear on the left side. So left side means it is x which will be determining the attributes. So in order to find the closure of x is denoted by x plus. So plus will appear in the superscript. So we have to determine each set of attributes where x appears on the left side of a some functional dependency, and then we will determine the set of all attributes that are dependent on x. So the input for such an algorithm is the set of functional dependencies on a relational R and set of attributes x, which is a subset of R. So here the things that are specified is F, where F is a set of functional dependency, R is a table, that is the relational schema, and X is the set of attributes. Then we have to find X plus. So the initialization step where the closure of X is first initialized to X. Then we will have a iteration repeat. This is the like just like a do while condition. So where this is similar to do, and this is the while condition. So which algorithmically, so we'll represent it using repeat and until statements. So until what is the condition, that is a closure x plus is equal to old x plus. So old x plus is a temporary storage. So in this particular one, in the beginning, so we will put old x plus. So old closure is initialized to x plus, and x plus is initialized to x, old set. Next, for each functional dependency that exists in F, what we have to do is, if y is a subset in x plus, then we have to add z to the x plus. So we have to repeat it for each functional dependencies. So the meaning of this is, for each functional dependency, so it is just similar to for looping. So what we have to do, we have to check whether the left side of a functional dependency is a subset of x plus. Okay, so if left side of a functional dependency, if it is present in the x plus is nothing but the closure. So if it is present, which means it is a subset, then for the closure we will add z. So that is union of z. That's it. So a very simple algorithm. So, and this is done for all the functional dependency, then one iteration will be complete. So after one iteration, we will verify whether there is any updation in the x plus, that is the closure. So if there is no updation, then this iteration will come out. If there is any updation in this particular step, then once again the entire process is repeated for finding the closure. So in this step, initially x plus is equal to x, then will store temporarily the closure in old x. Then for each functional dependency y determining z, we'll check, verify whether y is a subset of z plus. So if y is a subset of x plus, then we will add z to this. So here, if y is a subset, that if it is present in closure, it indicates that from x we can determine y, maybe in a single step or multiple step. So that is the meaning of this one. So yesterday we studied, if y is a subset of x, then x x will determine y. So if um, x contains y, or y is a subset of x, then we can imply based on the rule that x determines y. So similarly here, if y is being determined by x and y is determining z, the transitive property says that based on these two rules we can deduce that x determines z. So x determines z over here. If x determines z, it indicates in the x plus we have to add z. So that's why here x plus union z. So this is a very simple algorithm to find the closure of x under y. So equivalence of sets in functional dependencies can be established. So a set of functional dependencies F is said to cover another set of functional dependency E if for every functional dependency in E, it is also in F plus. That is, if every dependency in E can be inferred from F, then we can say that E is covered by F. So this is the coverage. If we can infer all the functional dependencies of E from F, then we say F is covering E, or alternatively E is being covered by F. So two set of functional dependencies E and F, we say they are equivalent if their closure is also equivalent. That is, E plus is equal to F plus. So if this is the case, then we say the two functional dependencies are equivalent. So if they are equivalent, it indicates that all the functional dependencies that exist in F and E are same. So equivalence means that every functional dependency in E can be inferred from F, and every functional dependency in F can be inferred from E. So E is equivalent to F if both the condition, that is E covers F and F covers E. So if both of them cover each other, then we say that the functional dependencies are equivalent. So minimal sets of functional dependencies. So just as we applied inference rules to expand the set of functional dependencies to arrive at the closure F plus, so it is possible in the opposite direction also, which means we can shrink or reduce the set of functional dependencies to its minimal form. The reverse process of finding the closure, it is called as minimal cover. So here, if f is a set of functional dependencies, then the closure is determined by f plus. So which means we are expanding f. So which means from each attribute we will try to find all other attributes which are covered by that particular functional dependency. Here in minimal cover, it is a reverse process. So if f is the functional dependencies that are known to us, then we will try to minimize it. So such that every dependency in f has a single attribute for its on its right hand side. Then we say that it is a minimal one. So at set of functional dependencies f, it is said to be minimal if there are if these three conditions are satisfied. So the first condition is every dependency in f has a single attribute on right hand side. So on the right hand side, for any functional dependencies x determining y, if single attribute is there on the right hand side, then it can be called as a minimal. Then we cannot replace any dependency in f with another dependency where y is a proper subset of x and still have a set of dependencies that are equivalent to f. And if any functional dependency is there where x determining a in f with y determining a, and y is a proper subset of a x. So if no such replacement is possible, then also we can say it is minimal. Then we cannot remove any dependency from f and still have a set of dependencies that is equivalent to f. So if these three conditions are met, then we say the functional dependency whatever we have, it is minimal. So first thing is single attribute on the right hand side. Secondly, we cannot replace a functional dependency. So it says it is regarding replacement. If one functional dependency can be replaced with another functional dependency, if the left side is a proper subset, then is a deletion of a functional dependency. If we can delete a functional dependency and still have a set of dependencies that are equivalent to f. So we cannot delete or we cannot replace and single. So if these three conditions are there, then we say it is a minimal set. That particular functional dependency what we have, it is said to be minimal. Then minimal cover. So the minimal cover is a set of functional dependencies. E is a minimal set of dependencies that is equivalent to E. So whatever is covered in the minimal, then that itself is called as a minimal cover. So minimal cover is a set of functional dependency E minimal that is equivalent to E. So next, let us look at the algorithm for finding the minimal cover. So input is a set of functional dependencies E. So E is a functional dependency that we are considering. So the aim of the algorithm is to find the minimal cover F of set of functional dependencies E. So E is our set of functional given functional dependency. For this set, we have to find the minimal cover. So minimal cover means then, so initially, so the set of minimal cover is initialized to E itself. Then replace each functional dependency X determining A1, A2 till AN in E by set of n functional dependencies, that is X determining A1, X determining A2 till X determining A1. So here we have multiple attributes. So all these will be divided into separate dependencies. So that is in step 2. Then in step 3, for each functional dependency X determining A, for each attribute B, that is the element of X, if F minus X determining A union X minus B determining A, if it is equivalent to F, then replace X yielding A with X minus B yielding A. So the meaning of this particular statement is for each attribute that is there in X. So X is a set of attributes. So for each attribute that is there in X, we have to determine whether if we remove that particular attribute, still the dependency holds or not. So if this is composed of three attributes, so let us call it as B, C, D are the three attributes that are there in X. then we'll verify whether removing B still this dependency holds or not. If this holds, then B can be removed. And then similarly, we will verify whether B comma D, that is removing C, whether this dependency holds or not. Or even removing D. So this also will verify whether these functional dependencies can be determined or not. So if it can be determined, then B attribute can be removed from the functional dependency, that is earlier X determining A. From this, B can be removed. For each remaining functional dependencies, X determining A in F, if F minus XA, if it is equivalent to F, then we will remove X yielding A. So for each functional dependency we have X determining A, we will verify whether if we remove this particular functional dependency from F, still if it is equivalent to F, then we will remove this. So this indicates that this is just an extra that we have added, or this is just an additional one without which also it is equivalent to F. So if removing this X determining A, if it is equivalent to F, and how to determine whether it is equivalent to F? So that is like this. So F, we have to verify F minus X yielding A if it is equivalent to F. So how to determine? Two, two sets are said to be equivalent if this covers this one and this covers this one. So previously we saw when we say two set of attributes are equivalent. So if this is equivalent, then this particular functional dependency can be removed. Then what happens? One functional dependency gets reduced. Okay. So consider this particular example in order to find the minimal cover for the following set of functional dependencies. So E is a set. So E contains B determining A, then D determining A, and AB determining D. So all the above dependencies are in canonical forms. So canonical means on the right hand side there is only one attribute. So if on the right hand side if two attributes are there, then we have to divide it. So if you observe here, on the right side only one attribute is there. Suppose if there was any functional dependency like this, y and z, if two attributes are there in the set, then we have to divide this into x determining y and x determining z. So this split we have to do when we have multiple attributes on the right side. But in our example, so we don't have any such cases. So if that is not there, then we say it is in canonical form. So according to the previous algorithm, the first step is over. So first step will apply only when the right side has more than one attribute. Then now we will look at the second step. In second step, we need to find whether any erroneous attribute is present on the left side. So in the first step, it is the right side. Second step, it is regarding the left side. So now, in the second step, we will consider only those which have multiple attributes on the right side and the left side. So in our example, so AB determining D. So here there are two attributes on the left side. So now we have to verify whether it is erroneous or not. Now look at those attributes A and B. Now here we have one functional dependency, that is B is determining A and AB is determining D. Now by augmenting rule, what we can do is for both the sides we will push B like this. Here also one B, here also one B. But here we know if we have double sets, then it can be written as B determining AB. Now if you observe B determining AB and AB determining D, here, this one. So now we can apply the transitive rule, that is B is determining D. Okay. So by transitive rule, B is determining D. So which means this particular functional dependency we can remove and replace it with B determining D. Okay. Now we have a set, let us call it as E dash. So after doing those two processes, let us call it as E dash. So now we have B determining A, D determining A, and in place of this we have B determining D. So this is one step. Now no further reduction in attributes is possible here, okay, because on both the sides now we have a single attribute on left side also. Now we will go to step 3. So in step 3 we will look for any redundant functional dependency. By using the transitive rule, if you see here, B determining A and A is not determining anything. But now if you look at here, B is determining D and D is determining A. So it is transitive. B determining D and D is determining A. So two functional dependencies are there and these are transitive, and hence we can write B is determining by A. Okay. So using these two functional dependencies, we can derive this one which is there in the set, which makes that B determining D as redundant. So this can be removed. So now we are left with the two functional dependencies. So we can call it as the F. So that is B determining A on B determining A can be deduced. So B determining D and D determining A. So this is our minimal cover. So what are the steps that we followed? So in the first step, so check whether we have a single set on right side. Then bring it to single attributes on left side. Then apply any transitive rule is possible. So only two functional dependencies are possible. So and this F and E are equivalent. So this is the final result. So the solution, so in the steps whatever we discussed is this. Okay. So let us consider one more example. So that is the functional dependency. Consider this. A is determining um, B, C, D, E, and CD is determining E. So let us consider these two functional dependencies. Okay, so let us call this as G. Set of functional dependencies, we are calling it as G. So in the first step, we will bring the right side to canonical form. So now we will have A determining B, then A determining C, then A determining D, and A determining E. Okay, and another one CDE, as it is, we will write CD determining E. So now the right side we have only one attribute, that will be our step 1. So that is step 1. So in the step 2 we have to bring the left side to one attributes if possible only. Now on each one of them, this one, here only one attribute is there. Here we have two attributes, but we have to verify whether this is erroneous or not. So we cannot, if we just consider the CD determining E, we cannot write C determining E or D determining E. So this is not possible. So and from these given, we cannot deduce this. See here, A is determining C and A is also determining E, but D is also determining E and A is being determining D. So we cannot substitute CD with any other functional dependencies. So neither C nor D is erroneous on the left side, because we cannot deduce C yielding E or D yielding E from the given functional dependencies, and we cannot replace it. So here no replacement can be done in the second step. So in the previous example we discussed the replacement was possible, but here the replacement is not possible because we cannot derive this. So this cannot be derived from the given functional dependencies. So and in step 3 we want to see if any functional dependency is redundant. So do we have any redundant? Okay. So let us see. In the third step, we have to verify whether any redundant is there. See, A is determining C and A is determining D and CD is determining E. So which means A determining E becomes redundant. See here. So A is determining C, then A is determining D also. So can we write like this, CD, because right side we can combine, and on the other side we have CD determining E over here. So this one. So now the transitive rule can be applied and we can write A determining E. So this can be derived, but in the set already we have A determining E, so which becomes redundant. So A determining B is redundant. So since it is redundant, we can remove it, right? So after step 3, our minimal cover minimal cover G will be like this: A determining B, A determining C, A determining D, and CD determining E. So this is the one. But now again the further minimization is not possible, so we'll just combine these and we'll combine the functional dependencies where right side left side is same. So A determining BCD and CD determining E. So this will be our final functional dependencies, so where we can reduce. So when you look at the algorithm, it may seem complex and the statements are such that you may not understand it, but if we look at the examples, so it is just that we are simplifying it. If we can derive any functional dependencies from other dependencies, then the one which we can derive becomes redundant because we can derive it from other functional dependencies. So we will eliminate them. So we will keep on eliminating such redundant functional dependencies to arrive at the minimal dependency. So that is called as a minimal cover. Okay. So we can stop here for today's class. So in the next class, so we shall discuss the properties of relational decompositions.